For this question, we have a stock that pays dividends, and the dividends keep increasing by 4%, and at an interest rate of 8%, we want to find the duration. So first of all, let us once again draw a diagram. So once again, this is a perpetuity. So we start off, so we're not given the amount of dividend that we receive. So we could start off with a certain number, let's say C. So the first dividend that we receive is C, and then it keeps on increasing by 4%. So the next is C times 1.04, and then 1.04 squared, and so on, all the way to infinity. So now we want to find the duration. So once again, let me write out the definition of duration. So times cash flow times discounting it back to time 0. So in our case, duration would be equal to, so once again we apply this formula directly. So we have our time, which is 1, times the cash flow C, times the discount factor of V. And then for time 2, we have 2 times, in this case now the cash flow is C times 1.04, and then times V squared. And then once again we do the same thing, 3 times C times 1.04 squared times V to the power of 3. And this keeps on going to infinity. So immediately you see a pattern over here. You have the powers over here keep on increasing. And then for the denominator, you have something that is essentially a geometrically increasing annuity. So we start off with V plus 1.04 V squared plus 1.04 squared times V to the power of 3, and so on. And it goes on all the way to infinity. So all the way to infinity. So first of all, immediately you see that the C's, they cancel out. So it turns out it's perfectly fine that we're not given the initial amount of dividends, because duration is just a ratio, so in the end it cancels out, so it doesn't matter what the exact value is. And immediately you see that the problem reduces to something like this. Times 3 times 1.04 squared V to the power of 3. So now we have two expressions to evaluate. We need to evaluate the denominator as well as the numerator. So for convenience sake, I'll call this A, I'll call the denominator B. So B seems easier, so let's try to find B first. So as you can tell, B is really, the denominator is really just a geometrically increasing annuity. So as always, this is why I keep telling you to memorize this formula. So now you can apply it directly. So for the denominator, K is equal to 4%, and then in this case this is a perpetuity, so this is going to tend to 0. So we have 1 divided by I is 8% minus 4%. So we have 1 over 0.04, and that's just equal to 25. So this is the denominator. And then for the numerator, it's slightly trickier because we have something that looks like this. So 2 times 1.04 V squared times 3 times 1.04 squared V to the power of 3. So this looks like an increasing annuity, but we don't have an interest rate over here because we have this extra 1.04 term. So in cases like these, we can't use these formulas to save ourselves time. We have to derive everything from scratch. So the first thing we can do to kind of make this easier for us to visualize is to multiply both sides by 1.04 so that the powers here, they will match. So instead of writing it like this, I'll write it like this. 1.04 times V whole square, and then 1.04 V cube. So now it becomes, this expression here becomes slightly easier to read. And then in cases like these where you have this common factor here, so when this is increasing geometrically and arithmetically, the way you solve this is essentially the same way how you would derive the formula for a geometric series. You multiply both sides by the common factor, and then in this case the common factor is 1.04V. So if I take this expression and I multiply by 1.04V, I'll get 1.04V squared plus 2 times 1.04V cubed plus 3 times 1.04V to the power of 4. And then I'm going to take the top expression, 1.04a, and then minus the bottom expression. Take this and minus this. And then you'll immediately see why I'm doing this, because there are no terms that correspond to this, so I can just write this out. And then for the square terms, you see that there are 2 over here, there's only 1 here. So after you minus that term, you have only one of these terms remaining. And then over here you have 2 of these terms and 3 of these terms. Once you minus it, you have only one of these terms left. And so the same thing keeps going on. So it becomes an infinite series of these 1.04 times v's. So it becomes a geometric series that goes all the way to infinity. So let's open a new page. So let's copy out what we have for the time being. So we have 1.04 and then times 1 minus 1.04v times a, and on the right hand side we have 1.04v plus 1.04v squared plus 1.04v to the power of 3 all the way to infinity. So one thing you can do is immediately apply the formula for geometric series, but what I'm going to do now is to take away the 1.04 from both sides. So now this becomes square, this becomes cube, and this becomes square. So you see that on the right hand side. Now that I take away this 1.04 on the right hand side, we get exactly the expression for geometrically increasing annuity, which is exactly the denominator over here. You see that it's exactly the same. And then we found previously that this is equal to 25, right? So the right hand side is just equal to 25. And on the left hand side we have this. So v is just 1 over 1.08. So the numerator a is just equal to 25 minus 1 minus 1.04 divided by 1.08. So you substitute this into your calculator. So you see that this is 675. So going back to the original problem, we're trying to find the duration, right? So we found that this is equal to 675, and then this is equal to 25. So once you take the ratio, plug this into your calculator, you see that this is equal to 27. So this is the duration.